Welcome back, students. Today we're going to be looking at section 11.2 on the multiplication and division of complex numbers. So in the last lesson you might have been thinking to yourself, what the heck good is this trigonometric form? Like, why the heck would we care to rewrite things with these sines and cosines? It seems like an awful lot more work. And, well, it might appear that way, but what it really does, the reason we want to do this is it really simplifies the multiplication and division of complex numbers. So if you recall, back in your Algebra 3-4 class, you would have learned how to multiply two complex numbers like these together. And if you remember all the way back, we would have kind of FOILed this out. So we'd get 10 minus 12i plus 15i minus 18i squared. And then we would have combined our like terms to get 3i. And remember that I squared is equal to -1. So that negative 18i squared turns into just plus 18. So that becomes 28 plus 3i. And you might have said, okay, that's not so bad. But what would we have? Think about how big of a pain it would be if you had to, say, multiply 10 complex numbers together. Ugh, that's a lot of foiling, right? So if there's a way to speed that up, that would be very much appreciated, and there turns out there is. So let's say that I have one complex number that's written in trigonometric form, and a second complex number, it's also written in trigonometric form. And let's multiply these two together. Using the rule that we used above, we're just basically going to be FOILing. So what I'll do is I'm going to pull both of those r's out front. Since you just have four things that are multiplied together, you can multiply them in any order you want. And then I'm going to FOIL inside. So I'm going to have cosine theta 1 times cosine theta 2 plus I cosine theta 1 sine theta 2 plus I sine theta 1 times cosine theta 2 plus sine, or I squared, sine theta 1 times sine theta 2. So what I'm going to do now is I see that I have two pieces that don't contain i's, because remember, I squared is equal to -1. And then I have two pieces that do contain i's. So I'm going to group these things together. So I have cosine theta 1 times cosine theta 2 minus, because remember the I squared is -1, sine theta 1 times sine theta 2 plus, and then I'm going to factor the I out, cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. And I'm going to look at what I have here. Because if you take a look at this piece, this should look familiar. Does anybody recognize this? Think all the way back to chapter 6. You can remember back that far. You might recognize this as the sum of angle, or the angle sum formula for cosine. And if we take a look at this, if you remember the previous one was the angle sum formula for cosines. This you should recognize as the angle sum formula for sines. So this then is our formula. And this is spectacular. Because if I multiplied 10 complex numbers together, I just multiply all 10 of their moduli together, and then I add their 10 arguments together, and I have this new r times cosine of this new modulus plus I times the sine of this new argument, and we're done. Right? So this is nice because it scales. Let's just do a quick example here. So say z1 is 4 times cosine of 172 plus I sine 172, and let's say z2 is 7 cosine of 13 plus I sine 13. And if I want to do z1 times z2, I'm just going to do 4 times 7 times sine of 172 plus 13 plus I times sine 172 plus 13, or really 28 cosine of 185 plus I sine 185. And if I really wanted to, I could type those into my calculator to get the decimal approximation to put that back in our standard form. So for example, 28 times cosine 185. But I got to be careful here because I know the last time I was using this, I left this in radians. So better change that to degrees. And I do the same thing for sine. So I get negative 27.89 minus 2.44i, depending on which form we wanted, whether trigonometric or the standard. That's pretty neat. What about division? So recall back from your algebra 3-4 days, if I had, say, the complex number 3 minus 2i divided by 5 plus 7i, to divide these two complex numbers, I needed to multiply by the conjugate of the denominator, which means I have to multiply the top and bottom by 5 minus 7i. So that means I'm going to have to FOIL in the top and FOIL in the bottom. So when I multiply in the top, I get 15 minus 21i minus 10i plus 14i squared. Now the denominator, you could FOIL that out, or you could take advantage of the fact that you really have just as a difference of two squares there. So you're going to have 5 squared minus 7i squared. Oops. So in the numerator, I notice that we can combine some like terms. So negative 21i and negative 10i become negative 31i. And remember that I squared is equal to negative 1. And same thing here. So that gives me 74. And if I simplify that, I'd have 1 minus 31i over 74, which I'd write as 1 over 74 minus 31 over 74i. Which again, for a single division problem, no big deal. But what if I had like z1 divided by z2 divided by z3 divided by z4 divided by z5, and I did this over and over and over again and had like a bunch of divisions all in a row, this would become like really tedious. Well, it turns out we can come up with a similar shortcut. So I'm just going to show you the shortcut and not the proof, because in the homework I ask you to do the proof or the derivation for this formula. And if you're wondering how to start, I would go back and look at how I started for the multiplication, because it's going to be remarkably similar. So if you notice, we're just dividing the r's and subtracting the arguments. So again, the two moduli are divided and the arguments are subtracted. So for example, if I have a z1 that's 14 cosine of pi over 3 plus I sine pi over 3, get my extra parenthesis in there, and a z2 that's 2 cosine pi over 7 plus I sine pi over 7, and I want to divide these. Let's use a color here. So z1 divided by z2. So I'm going to have 14 divided by 2 times cosine of pi over 3 minus pi over 7 plus I times sine pi over 3 minus pi over 7. And then to subtract those two fractions, we need a common denominator. That common denominator would be 21. So I'd have 7 pi over 21 minus 3 pi over 21, which would give me cosine of 4 pi over 21 plus I sine 4 pi over 21. And again, if I wanted to, I could convert this into standard form very easily with my calculator. So this time I got to change my mode back to radians, because last time we were in degrees. So I'm going to do 7 times cosine of, and then I like to do mine with, when I have the fraction, to do that fraction command that we've done before. 21. And then we'll do the same thing with sine. So I'll just call that same command line and go edit the sine in. So that's everything we need. So this is about 5.78 plus 3.94i. Depending on which form you wanted, whether trigonometric or standard. And that's it. So now that we've finished this lesson, you guys are ready to do 41 through 64 on the homework. I know, it's a lot, but the lesson was short, so that's your payoff. And by payoff, I really mean trade-off.